Well, hello, my name is Germán Vidal. I'm going to present this paper on reversible tensor writing. So the paper was presented at the first international conference on formal structures for computation and deduction. And this is a joint work with my colleague Adrián Palacios and Naoki Nishida from Nagoya University in Japan. Well, what's reversible computation? So basically we say that a computation principle is reversible if any standard or forward computation can be undone by a finite and deterministic method. Well, the second condition, determinism, is not always required, and we could find less strong alternative conditions, but in this work, for simplicity, we will require determinism, finiteness and determinism. Okay? So, well, there are many applications of reversibility. A popular application is debugging. So we can find a debugger like can do, where when an error is spotted, then the user can go backwards in order to look for the source of this error. Okay. We could also consider another application for enforcing fault tolerance. So we could, for instance, think of defining sort of safe sessions, typically in the context of a concurrent and distributed programming language. So the idea is to have a session with a number of actions so that if one of them fails, then we can go backwards and undo the effects of the previous sentences in this session. Okay? So there are many other applications like quantum computing and many others. And if you're interested, you can find more information in the website of the Cost Action IC 1405 on reversible computation. Okay? So in this work, and well, this is quite a popular approach, we follow what is called a Landauer's embedding. So the basic idea is that any irreversible computation can be turned into a reversible one by storing the history of the computation in each state. So we have a state, and in this state we always include a list with the information of the previous states. So this is obviously reversible. Of course, this information can be huge in a long computation. And in practice, we try to minimize this information as much as possible, okay? Storing only what is really necessary for that, for going backwards. So in this particular work, we consider tensor writing, a computation principle that underlies many rule-based programming languages. It's true that in this context, there exists an inverse relation of the standard tensor writing relation. But unfortunately, this inverse relation is non-deterministic, is in general non-deterministic, non-confluent, and non-terminating, which makes it basically useless in our context. So, the aim in this paper, in this work, is to define a reversible and conservative extension of tensor writing. Okay, then let me introduce what reversible tensor writing is. So, I will start with a very simple example. In this case, this is a tensor write system defining the addition of natural numbers, built from 0 and successor, and a function first that takes 2 arguments and returns the first argument. Okay. So in the following, we label the rules with one of these symbols. Okay, beta 1, beta 2, beta 3 in this case. And here you can see a reduction, a possible reduction, it's not the only one, but a possible reduction for this term, first of the addition of 1 and 0, okay? The selected regex at each step is shown in blue. And well, if we want to go backwards, that is, we want to start from s of 0 and go backwards to the initial term. This is in principle not possible, at least not in a finite and deterministic way, for several reasons. So the first one is that we have overlapping right-hand sides, this variable y and this variable x, unify with all the right-hand sides. Okay. Therefore, if we want to apply a rule backwards to s of 0, we don't know whether the rule that we should apply is beta 1 or beta 3, because both of them are applicable. Okay. Moreover, even if we know which rule should be applied, we still don't know to which position, because we could apply the first or the third rule to 0 or to successor of 0. Okay, both possibilities are can be done. On the other hand, even if we know the rule and the position, there's still something that we don't know. Consider, for instance, the last step with the third rule. Okay, if we go backwards, there is one rule here, this rule y, which is called an erase variable because it occurs in the left-hand side but not in the right-hand side. Therefore, when we go backwards, we don't know the value of this y. Okay, so these are basically the three pieces of information that are required to go backwards in terms of writing: the rule, the position, and the bindings of the erase variables. Okay, so in particular, what we propose is to add trace terms to the computation, to a reduction, and each trace term has this form. So it contains the label of the applied rule, the position of the reduced term, and the bindings of the erase variables, if any, otherwise just an empty substitution. So we are defining basically a Landau's embedding, as I mentioned before. Well, let's consider the example again. So now we work with pairs. The first component of a pair is the term, the same term as before. And we have a second component, this one, which is a list of trace terms of the form that I have just shown. Okay. So now the first step, the reduced term is the same, but we add this information to the trace, to the history of the computation. So we have applied rule beta 2, position 1, and there are no bindings because there are no erase variables in this rule. Okay. Second step is similar, and for the last step, observe that we have some binding here because in the third rule we have an erase variable. So this is the final result now. It's not only s of 0, but also this list of trace terms, and therefore the computation becomes trivially reversible. Okay, we have all the required information here. Okay, we know that we should apply a rule to the entire term because we have epsilon here. We should apply the third rule, beta 3, and we know the value of this erase variable, therefore it's completely deterministic. And of course the process is always finite because we perform one step backwards for each element in this list. Okay, so as we wanted at the beginning, as I mentioned at the beginning, we are producing a finite and deterministic method to make ternary writing reversible. Okay. Well, actually, in this work, we don't consider unconditional systems, but conditional ones. Okay. In particular, we consider deterministic oriented 3C TRSs. So oriented means that the rules have this form. So we have a condition in each rule, could be empty, of course. And in this condition, we have a number of equations which are basically reachability problems. I mean, the equations are oriented, which means that S1 should be reduced to T1, S2 should be reduced to T2, and so on. Okay. The second condition, 3C TRS, means that the variables in the right-hand side of a rule in R should occur either in the left-hand side or in the condition of the rule. Okay, and this bar on top of the terms means a sequence. It's a shorthand to denote a sequence from S1 to Sn and T1 to Tn. Okay, and finally, the rule should be deterministic. So intuitively speaking, determinism means that there is a fixed left to right way of reducing this rule. Okay, so look at this picture here, this diagram. So if we know the value of x, that means that we can start reducing the first equation in the condition, and then after reducing the first equation, we know the value of variable z. Therefore, we can start reducing the second condition to w. And if we know w, then we can return the result of applying this rule. So this is basically what determinism means in this context. It doesn't mean that rewriting is deterministic. The rewrite relation can still be non-deterministic. Okay. So when we consider conditional systems, there is one very obvious first extension that is required. So for trace terms, we need to add a fourth component, which is a sequence with the traces. That is the list of trace terms associated to the reduction of each equation in the condition of the rule. Okay, so we should also store this information here in the trace terms. There is a second difference which is a little bit more subtle, which is related with the bindings that we need to store in each trace term. Okay, so before we only store the bindings of the erased variables. Consider this rule. Okay, so there is a variable here m that doesn't appear in the right hand side or in the condition, this variable m. Therefore we should store this binding, and this is the same as in the unconditional case because this is an erased variable. Okay, but that's not enough. There is a second kind of binding that we should store, and the reason of this why we need these bindings is because when we apply the rule backwards, it should also be deterministic. In other words, we need, for instance, consider in this rule is deterministic in both directions, forward and backward. Say if we start with the value of w, then we can start reducing backwards this equation, then we know the value of z, then we can start reducing backwards this equation, and with the value of x we know we can return the original left hand side. Okay, or in other way, you can consider that if you switch the elements of each equation and you switch the elements of the left and right hand sides of the rule, then the resulting rule should be deterministic. And if it's deterministic, we don't need to store any other bindings. Okay, but if this is not the case, as it happens in this rule, then we need to store some bindings, some additional bindings. So consider the situation in this rule. If we know the right hand side, so we are applying the rule backwards, so we know the value of w here, so we can start reducing this equation backwards, so we know the value of y, but now we cannot start reducing this equation backwards because we don't know the value of x. Okay, therefore we need to store this binding in order to ensure that the reversible computation is still deterministic. Okay. Well, and the two main results in this part of the work are these ones. On the one hand, our approach is a conservative extension of rewriting. Therefore, we have a reduction from S to T in some oriented deterministic 3 CTRS. Then we know that there are, for any trace pi, and we know that there exists a trace pi prime such that a reversible rewrite relation exists that we denote with this arrow here. Okay, this is actually quite a straightforward result. Reversibility is not so trivial, and in this case what we have proved is that for each forward derivation there exists a corresponding backward derivation which is deterministic and thus confluent to and terminating. Okay, these are the main results of this reversible extension of tensor writing. Okay, in the second part of this paper, we introduce an alternative approach to reversibility in tensor writing. So basically here, we aim at compiling this reversible extension of rewriting into the rules of the system. Okay, so basically, given a rewrite system R, we want to produce two new rewrite systems, two instrumented systems, RF and RB, such that every forward reduction with the original system is basically equivalent to a reduction, to a corresponding reduction using a standard tensor writing with RF, and any backward reduction, okay, with the original system can be or is basically equivalent to a corresponding reduction with a standard rewriting using RB. Okay, so we don't need to consider an extended version of tensor writing, so we can keep the standard tensor writing relation and just consider these two instrumented systems, depending on whether we want to go backwards or forward. Okay, unfortunately, in this approach, dealing with positions is really hard, because the positions of the selected redexes is dynamic information, and therefore in our approach we have to get rid of positions in some way. Okay, so for this purpose we introduce a new class of systems, a restricted class of systems that we call basic CD CTRSs. So in this case, intuitively, this is a subclass of the previous class of rewrite systems, conditional rewrite systems, in which both the right-hand side R and T1, Tn are constructor terms, okay? And the remaining terms are basic terms, which mean that they have this form, where f is a defined function and C1, Cn are constructor terms, okay? And the nice property of these systems is that it's enough to consider reductions at topmost positions, okay? Therefore, since the position is always epsilon, is always the topmost position, we don't actually need to store it. And for this class of systems, we can get rid of positions, which opens the door to consider a compilation, as I mentioned before, okay? And well, we do that with a loss of generality, in the sense that we provide a flattening transformation, sort of pre-processing transformation that you can find the details in the paper, from the original system that we considered before to this particular class of basic CDC TRSs, okay? Yeah, and as I said, I'm not going to introduce this flattening transformation. It's actually not difficult at all, but you can find the details in the paper. So let me show you the transformations with some example. So this is the original system, the same that we have considered before, defining addition and the function first. First, we have a first transformation that we call injectivization, this one. So the idea here is basically, so we introduce fresh names for the functions with this superscript I, okay? The left-hand sides are the same. We are not changing the left-hand sides, okay? And for the right-hand sides, we are introducing pairs. The right-hand sides should always be a constructor term, and now we have a pair with the original constructor term, and the second element in the pair is basically a trace term as before, okay? So for the first rule, we have beta 1, just the label of the rule, because we have no condition and we have no erase variables, okay? For the third rule, we have beta 3, the label of the rule, and y, because there is one erase variable, so we need to keep the value of y. And for the second rule, we have no erase variables, but we have a condition. Therefore, we need to store the trace of this associated to the reduction of this equation in the condition here, in this trace term, okay? It's actually not too difficult. And then we can also produce an inversion of this system, which in this case is trivial because of the form that it has. So it basically, what we basically do is to switch the left and right hand sides of each rule, and the same for each condition. So you can follow the different colors, and you can see that producing this inverse system is quite easy, okay? So now we have two possibilities. We can apply reversible term rewriting and the first initial system, or we can apply standard rewriting with this system if we want to go forward, or we can apply the rules of this system if we want to go backwards, okay? So we have, as I mentioned before, we have compiled this reversible extension into the systems by instrumenting them with some additional information, okay? Well, conclusions. Well, first, to summarize, we have introduced a reversible extension of term rewriting, of conditional term rewriting to be precise. Then we have defined two transformations to instrument the original source system, the original conditional system, so that the standard rewriting becomes reversible using these systems. So we don't need to actually consider an extension of the rewriting relation. We can just consider a standard rewrite relation on these instrumented systems. And finally, we have applied these transformations to some problems. In particular, in the paper, you can find an application of these injectivization and inversion transformations in the context of something called bidirectional program transformation, okay? So for future work, we want to look for conditions that allow us to remove as much information as possible from trace terms. So for instance, if the right-hand sides of the considered rules are non-overlapping, then rule labels are not really necessary, okay? And we can remove them, we can get rid of them from trace terms. There is actually a characterization of a class of systems called biorthogonal, introduced by Abramsky. And in these biorthogonal systems, well, these systems are basically systems which are orthogonal, but if you switch the left and right hand side, they are also orthogonal. Okay, so for these systems, you don't really need anything. So you can remove completely the traces from the systems, and they are still reversible. Perhaps something in between is more interesting than these are the extremes, to keep all the required information, to keep nothing. Unfortunately, biorthogonal systems are very restrictive, and therefore something in between is more reasonable. Okay. And on the other hand, we're also working on an extension of what we have done in this paper for a concurrent functional language like Erlang. So what we have done in this paper transfers smoothly to the sequential part of a language like Erlang, because Erlang is a functional language. But we also need to the concurrent features of the language, and this is a completely different challenge. And well, if you're interested in this problem, in this extension to a concurrent language, I encourage you to look at our Lobster paper. So thanks for your attention.